Okay, so this revision video is just going to take you through some of the main elements that appear repeatedly on past paper questions regarding the ICT theory content. There'll be 4 instalments of the videos. This first one is going to focus on chapters 1 and 2. How to use the video would be to go through listening to the discussion, obviously, but using your notes. And if you come across something that you're unfamiliar with, words or examples or diagrams or theories, just pause the video and add to your notes from this slide. Most of the content here has come directly from ictlounge.com, which you can use, obviously, to go into more detail if you want to look at things from a broader perspective, but I've just selected out the things that I think are repeatedly used in exam papers. So let's focus on chapters 1 and 2. Chapter 1 is types and components of the computer system, and it's broken down into 5 elements: hardware and software, components, operating systems, types of computer, and emerging technologies. I'm not going to go through everything in detail. There's a lot of stuff here that is quite common sense, that you just have to think about how you phrase your responses and how you phrase your answers. But I am going to pick out the things that appear, as I said, regularly in past papers. So we start with hardware and software. One of the elements that you have to be prepared for is that they may ask you to define hardware and software, and you'll all in your heads think that you know how to do that or you know what it means, but do you know how to define it? So just be familiar with these key terms, okay? Hardware is all of the physical parts of the computer that you can see, touch or pick up, whereas software consists of coded programs for controlling the operation of the computer or processing of electronic data. Now, it's also important to be aware that software is split into 2 elements. You have system software and you have application software. So system software is the types of software that include operating systems or the utilities that allow your system to run smoothly. This could be things like antivirus or disk cleaners or the OS itself, the operating system itself. These system softwares often manage the computer's resources. They tell the computer how to operate, how to work. Okay, they're running in the background. You very rarely see these, the system software. Whereas the application software is the programs and the apps that you use on a day-to-day basis. These are used to produce an output or to process data, like word processors or spreadsheets are examples of application software. So anything that we've done as one of our 6 elements of skill for the practical tasks would be examples of application softwares. Be aware, try to avoid using brand names. Notice I've not said Microsoft Word, I've said word processors. And I've not said Excel, I've said spreadsheets. The exam board prefers you to not use the brand names, but rather the type of software. Okay, looking at the main components of the computer system, you need to be familiar with what is inside the computer system and generally what those components add to the running of the system. So in the syllabus, we're required to be familiar with these 8 sections: motherboard, CPU, RAM, ROM, graphics card, sound card, peripherals, this is input and output devices mainly, and storage devices. So the motherboard is a large circuit board which enables all of the other internal devices to communicate together because they all connect onto the motherboard. So the motherboard is sort of home base for all of the other internal components, enabling those internal components to communicate using a very basic bus network. There's like a tiny little mini bus network on the motherboard that sends information backwards and forwards up along the circuits to all of the other elements. Okay, so this is just like home, so that everything can connect within this system. It causes the base. It provides the base circuits. The CPU stands for Central Processing Unit. It's quite often referred to as the brain of the computer. These come in different speeds and different hertz, so you can get much more capable CPUs, the more expensive ones that can process data at much faster rates. They have brands, so Intel is one of the classic brands that you find for the computing, for the central processing unit. And basically what this function does is it is the main chip that actually does the thinking, shall we say, so the processing element when it comes to breaking down the task of what's been asked to do, whether that's to send data to a certain place or to calculate a function or so on and so forth. These different tasks are thought through by the central processing unit. It's probably one of the most expensive parts and elements of the inside of your computer. And then we've got the RAM and the ROM, which are both elements of internal storage but have different functions. Your ROM, your read-only memory, is memory that does not get overwritten. It is the system where your operating system and the main instructions for how your computer should boot up, that exists in the ROM. It is non-volatile. That means that when your computer gets turned off, the ROM stays where it is. You don't save to the ROM as such. This isn't where you put your work. This is the core memory of the computer that tells the computer how to behave. It's, as I say, it's where your operating system would base itself from. Whereas the RAM, the random access memory, this is like your capacity for thought in the computer. So the random access memory enables the computer to do multiple things at one time, to have multiple windows open, or to be flicking between different systems and different softwares. The random access memory means that when you flick from a Word document onto the internet to do some research, you come back to the Word document still has your text in it. That text may not have been officially saved to your hard drive, but it's still inside the software, and that is your random access memory. But if you then turn your computer off without saving and you come back, the likelihood is that work will be gone. That's because random access memory is volatile, so it is wiped whenever you turn your computer off. Now, some software have like a backup system for this to prevent data loss, where there'll be an automatic save. But that's aside from RAM. The function of RAM is this ability to have a memory for what it's doing at that moment in time. So it can switch between screens and it can do multiple things, and it doesn't forget what you've done in a previous screen. That's your random access memory. Very, very useful for high functioning computers. If you're looking to improve the speed and the performance of your computer, you're probably looking to increase your RAM. The graphics card and the sound card, for those of you who are into gaming of any description, will be familiar with these. The graphics card enables the computer to display images on the monitor, and the sound card enables the computer to produce and process sound. Now, all computers that use a graphical user interface will have basic versions of these, but people can actually buy upgrades, because if you're producing high quality graphics, like for example if you're an architect and you're working on design blueprints for a for a house or a building, or if you're a web designer, or as I said, if you're a gamer of some description, then you're probably going to want to increase the image quality of the graphics that you have on screen. And the same if you work with music, or if you work with sound recordings of any description, you probably want to improve the quality of the basic sound card that is provided with most PCs today and most laptops. And you can do so by buying upgraded graphics cards or sound cards. We'll go into peripherals and storage devices a little bit later, because peripherals are all about input and output, which we're going to do in Chapter 2, and storage devices gets covered in Chapter 3, so I won't go through those now. Classic question is to remembering the difference between RAM and ROM. So remember, if the contents are lost when the computer is turned off, that's RAM, because the computer contents are not lost when the computer is turned off, that's ROM. Stores instructions that tell the computer how to start up, that's the ROM. okay? Stores data and programs currently in use, that's the RAM. Your computer will perform faster with more of this, that's your RAM. This can be written to or altered and read from, that's the RAM. This cannot be written to or altered, is only read, that's the ROM, okay, because you can't change the instructions of how to start your computer up. Stands for random access memory is RAM, and stands for read-only memory is ROM. Okay, going on to 1.3, talking about operating system, the OS of the computer. There are three types of operating system: the command line interface operating system, the graphical user interface operating system, and a touchscreen operating system. Now, again, there are brands that you'll be familiar with. Windows is an operating system. Linux is an operating system. Apple has its own operating system, the iOS, or the whatever version that they're currently up to. But all of these operating systems will have some main functions, and here are the 10 main functions listed. You don't need to know all of them, but be confident in naming at least 2 or 3. Okay, so the operating system accepts inputs from the mouse or the keyboard, recognizes the peripheral devices like external hard disks, pen drives, webcams, etc., allows application software to communicate with the system hardware, loads and runs software applications, handles system problems and alerts. For example, if a printer is jammed or can't print, the operating system will stop the print job and alert the user with a warning message. The operating system also sends outputs to the monitor or the printer. The OS manages files and folders in the system. The OS shares out system memory efficiently, so decides how much memory to assign to a particular task. The OS also manages system security, so it will allow passwords to be added or changed, creating new users and access rights, and manages the moving of data to and from hard disk. So if you're not sure on some of the functions of the operating system, pause the video there and note down 2 or 3 of these different functions of the operating system, because that is another classic question that does come up from time to time. Once you've done that, we're going to move on to the types of operating system. Okay, so we have the command line interface. This classic view, keyboards used to enter the commands into a command prompt. Command line interfaces do not make use of any images or icons. All the user sees is a plain black screen. They're very complex and they're generally used by experts. Because there's no graphics used, they require very little in the way of computing power. Now take a look at the advantages, disadvantages here. So because the user communicates directly with the computer, they actually have quite a large range of control, so a wider range of commands can be used, and it needs very little computational power. They can run on very old computers. You don't need significantly impressive CPUs or RAM capacity to run a command line interface. However, the user must remember complex commands, there's lots of typing needed, and there is a high chance of error because all you need is one spelling mistake or one missed punctuation mark and your command is not going to work. Then we have the graphical user interface. The features of the graphical user interface are simplified down into the acronym WIMP, W-I-M-P, Windows, Icons, Menus and Pointers. So the availability of opening different windows on the screen, icons like the file icon or the folder icon, menus, so when you click on Start and you gain a menu, or when you click on File and you gain a menu, and pointers, the availability of you to control a mouse and move your pointer like I am here, to be able to select things on the screen. This is the most common of user interfaces today. Quicker to enter commands, easier to enter the commands, and less chance of making an error. You're just clicking on the image that you want. But there's a smaller range of what you can do. For example, you might be trying to change the language of your keyboard, and you're sat looking at your home screen, and you can go into startup and things like that, but you're looking for where to do that because you can't automatically see the icon for language or region. Whereas if you're in the command line interface, you can just simply type that command. You don't have to look for anything. But on one particular screen, you can't have every single potential command available in a graphical user interface. Graphic user interfaces require more computational power and more electricity as well to run. So they do require a more advanced device. And then we have the touchscreen interface. Now, essentially, even though this is quite often called a post-WIMP interface, as in post-WIMP, touchscreen interfaces do still tend to have windows and icons and menus. The only thing they don't tend to have is the pointer, because of course the touchscreen takes away the need for the mouse. On mobile phones and tablets, you would use your fingers as the control. And we have these main elements of that: pinching, rotating and swiping. So pinching your fingers together across the touchscreen to zoom into an image or to zoom out. Rotating, when you move your fingers up whilst the other moves down to rotate an object or an image, or to, say, even navigate through Google Maps or something like that. And swiping, when you swipe your fingers across the touchscreen to scroll through a document or turn the page. Now, we're all familiar with Macs, and Macs on their touchpad on the laptop will use some of these touchscreen interface features as well. They have this kind of strange hybrid between the WIMP and the classic touchscreen interface. But this one is referring to where you don't have a mouse or a touchpad, so it's mobile phones and tablets mainly. Okay. The last one in Chapter 1 would be emerging technologies: artificial intelligence, biometrics, robotics, quantum cryptography, computer-assisted translation, 3D and holographic imaging, and virtual reality are the main emerging technologies that the syllabus refers to. Now, I'm not going to go through all of them. I'm just going to summarise the uses and the impacts of the first three. If you want to spend some time going over the others, there is some great notes on this in ICT Lounge. So, if we would talk about artificial intelligence, where is it used? Mainly today, game playing, expert systems, languages, and robotics. So in game playing, artificial intelligence has been used to create computers that can challenge things like chess players. Okay, in '97, a computer named Deep Blue defeated the world champion in a game of chess. And this was about programming the computer to be able to learn from the moves that it was making, and therefore to be better advised in the next move it was going to make. Now, the word artificial intelligence is quite contentious for a lot of scientists. The idea of intelligence should be spontaneous thought without needing to be programmed as such. And computers at this moment in time all require a level of programming. But then we could compare that to teaching children. All children require a level of input from an adult, at a young age, whether it be to speak or to walk or whatever else. And then eventually they develop the level of independence where they don't need that level of input. So whether or not you agree that this is an example of artificial intelligence, the exam board uses it as one, so we accept that in that sense. Same for expert systems. This is a separate topic that's taught later on in the course, but these are computers that have been programmed to make decisions based upon information given to them, so like medical expert systems for diagnosing patients or diagnosing the problems with a car engine and those kind of things. Languages. Understanding human languages as they're spoken to them. Massive improvements in translation systems, not only looking at the direct translation of a word, but also inflection in the voice, meaning, sarcasm, and so on and so forth, and how computers can be taught what we are saying and what it actually means. And robotics. So robotics, you will use artificial intelligence when machines are used to imitate humans or to imitate other roles and other jobs. And these types of artificial intelligence is whereby the computer is given a certain set of parameters, and from that the computer runs a series of tests, for example, and from those tests is able to develop the actual thought process itself further. So what are the impacts of artificial intelligence? Well, some of the benefits that we have are things like accurate prediction of weather, increased leisure time. We have safer transport because we've got cars that can self-park using sensors, and there's already tests of cars that can drive themselves. Now, whether that makes safer transport or potentially more problems is yet to be seen. But we could argue it both as an advantage or as a disadvantage. So that's an interesting point. Increase personal safety, so alarm systems using artificial intelligence to protect homeowners and against intruders, automatic systems that alert the police and so on and so forth, and improved medical care. We've already got amazing artificial intelligent robotic surgery assistants used to deal with very, very delicate, fine work in complex surgeries. And artificial intelligence, as we said before about the expert systems, improving medical care for people who maybe don't have the expert doctors available to them. So small health clinics in developing countries where it's not always available to have a specialist. So we've got lots of impacts. Remember, you're likely to be asked about the impacts more so than how it works, because this topic is essentially about emerging technologies for people and how it's going to change the world. Okay. Biometrics. Fingerprints, eye recognition, face recognition, voice recognition. We see elements of this now today in everyday technology on mobile phones for unlocking your screen. You know, you can get laptops which have a fingerprint scanner now rather than a password, and more secure buildings, more high-profile security entrance buildings like government buildings and things like that will use biometrics as security measures for gaining entrance. So there's lots of opportunities within biometrics. And of course, biometrics will improve an awful lot of opportunities. So things like security at airports, for iris recognition used in some airports. This is linked to the RFID chip that gets put into your passport, and then you have to stare into the automatic customs gate. That's using biometrics to scan the face, the shape of the face, or the iris of the eye, to compare to the image stored on the system from the passport. Increase building security. You know, you think how often you as students lose your access keys into school. Well, it's much more difficult to lose your fingerprints. So we have got improvements in building security there. They're less easily lost and much more difficult to forge. Reduce car theft. We've already got some modern cars today on the market that use fingerprints to unlock doors or start the engine. This means that doors would not unlock for a print that is not recognised and makes the car harder to steal. But it does mean that you have to program the car if you have multiple drivers. So if you've got a family car that's used by mum and dad and, you know, older sister or whatever else, all of their data has to be input into the system. And, you know, you want to lend the car to granddad or to uncle or whatever else. It's not as easy as just lending the keys because that person's data isn't input in. And more secure mobile phones, as I said already, we can see biometrics being used as a method of securing mobiles. Robotics. So robotics are used for dangerous jobs where could damage, harm, or kill people. Like disposing of bombs, like using toxic spray paints, or any kind of painting or use of chemicals that could be considered damaging. Cleaning up nuclear waste, you know, fairly extreme examples, but all of which previous to robotics would have had to have been completed by people. Exploring extreme environments, like geographers for volcanoes, science researchers looking in the deepest parts of our oceans and things like that. People would struggle to visit a lot of these environments. Repetitive manufacturing jobs, from a business perspective, robots are far more productive, far more efficient. They don't need wages, they don't take breaks, they don't call in sick, they're never late to work, you know, they can work 24/7. And they don't there is a reduction in human error there. Once the robot is programmed correctly, it will repeat the same task over and over again in an identical way. So really, really useful there. Although the other problem that you have is that that this does cause redundancies in the loss of jobs, and so you do have a de-skilling of people. And things like moving heavy objects, warehouses and factories will often use robotics now to move stock around. There's even examples in Japan where the healthcare industry is developing robotics, wearable robotics, to provide with for nurses, to help nurses who are lifting and moving patients, to enable them to do the job with less people, but to have the support of robotics there. Okay. And the impacts of robotics, similar to the impacts of the previous examples, increase in personal time if robots can do the job. More efficient manufacturing, so for business we've got a lot of benefits there when more products can be produced at a lower cost. There is a loss of jobs associated with robotics, although robotics will create certain jobs like the programming and the maintaining of the robotics. There's not as many of those sector of jobs as there are the jobs that the robot is replacing. So if you think about your automatic checkouts at the tills in the supermarket, if you think about robots in factories and robots in warehouses, there are far more of those jobs being lost than the new jobs being gained for robotics. And safer working environments, you know, people can safely carry out tasks that are safer for them to do, where robots can carry out tasks that are too dangerous for humans, and there isn't a risk factor associated to it. Okay, so this takes us through chapter 1. I'm going to start chapter 2 now. If you need to take a break, just pause the video. Okay, so in chapter 2 we've got input and output devices. And I'm just briefly going to go through these because, again, it's fairly common sense stuff. We've done it repeatedly, but I'm just going to focus on the things that do crop up in exams. Okay, so 2.1 input devices and their uses, 2.2 direct data entry and associated devices, and 2.3 output devices and their uses. Okay, so what's the difference between manual input and direct data input? So remember, manual input is the basic stuff that requires full human interaction. A keyboard, a numeric keyboard, concept keyboard, etc. They all require a human being to physically enter the data into the computer. It's an input device. Now, remember, the concept keyboard is, well, if we have the regular keyboard, what you're looking at in front of you on your computer now. Your numeric keyboard would be things like the pin code keyboard on a chip and pin device. That would be a numeric keyboard. A concept keyboard is where the letters or the numbers are replaced with shapes or icons. So, for example, when you go to a fast food restaurant and you have the on-screen selection where you pick your meals, you don't type anything in, you're picking pictures of what you want. That's a concept-based keyboard. Mouses and pointing devices, graphics tablets, remote controls, joysticks, microphones, webcams and digital cams. Direct data input requires less human interaction. There still needs a person to do something, but there is an element of automation in the direct data input. So like a magnetic stripe reader where you swipe your card along the side of a till screen, or where you swipe your card to gain entry to a secure area, that's reading the magnetic stripe. the chip reader part of the chip and pin reader, as I was saying, the pin section is actually a numeric keyboard, but the chip section where it reads the data chip, so all you do is put your card into the reader and then type in your pin and the chip is read by the reader. Barcode readers, barcode scanners. RFID stands for Radio Frequency Identification Device. We will cover that later on. Optical mark recognition, looking for things like multiple choice tests. Optical character recognition, so reading the name and the amount written on a bank check or on a questionnaire form. And MICR, also used for bank checks, looking at the magnetic ink character recognition. These three types are all essentially filled out on paper and then fed into a very specialist scanner, which is reading for either the mark in the correct place or the characters, the letters of the handwriting to convert that into text, or is looking to recognise the magnetic ink and associate it. Okay, so what about sensors as input devices? These are far more automated even than direct data entry. You actually need almost no human interaction for temperature systems. Sorry, for sensor systems. And we've got our list of types of sensors here: temperature, pressure, light, sound, humidity, moisture and pH, and what examples of what they might be used for. This is quite a common question as well that comes up, so if you're not familiar with how these different systems are used or the examples of what they might be used for, pause the video and just make a couple of notes there on the uses for those sensors. Okay. Two classic questions that come up are about the different types of monitors and the different types of printers. So I'm not going to go through all output devices because I think you're fairly confident in the difference between input and output devices, but I am just going to very briefly describe the different types of monitors and different types of printers. So these are the two main examples of monitors used today. CRT monitors are almost phased out now. We very rarely see them. It stands for a cathode ray tube. And what that means is that there are tubes of light inside the box that are being bounced from from almost like a torch at the back of the box onto the screen. They're a much older model and they're far bulkier than new monitors, but they are quite cheap to buy. You actually get a better image quality on a cathode ray tube because the light can actually produce a higher range of colours on these. And the other thing that's better about the image quality is that you can view the image quality from different angles. You can actually see what's on a CRT monitor regardless where you stand around it in angle. And one of the problems with them is that they actually get very hot because they have this torch that produces the light at the back of the box. It's not unheard of for these to catch fire as they get very, very hot. A TFT is the alternative, which is known as the thin film transistor. Now sometimes these are LCD, liquid crystal display screens, or LED screens and things like that, but they are essentially different methods of this flat screen. They're used today on modern laptops and mobile phones, as well as any kind of television or screen, things that you want to mount on the wall. If your TV at home is mounted on the wall, then it's going to be one of these thin film transistors because they're very thin and they're portable, which enables you to, for example, mount it on the wall. The other benefit of the TFT screens is that it emits much less heat and no or much less radiation than these examples. However, the picture quality is lower than the old CRT tubes, and you can't clearly view these what's on these screens from all angles. If you're not stood directly in front of it, it's very difficult to see or read what is on a TFT screen. So that's one of the issues with these. They are more expensive, although because they're so common today, that price is reducing and becoming more reasonable. What about printers? Do you know your difference between your four printers? Laser printers, inkjets, dot matrix and plotters. So the laser printer, very high output, really fast prints, brilliant for multiple copies, and it's very quiet. Toner is used in these laser printers rather than ink. And toner is like a fine powdered dust which sticks to the paper through heat. And the toner is much cheaper per page, although it is quite harmful to the environment. So toner is not a particularly pleasant item. It's quite toxic. So when it comes to the laser printer, they're quite expensive to buy, but much cheaper to run. The actual running costs per page runs are very cheap. Whereas the inkjet printer, quite cheap to buy these, however, they are much more expensive to run because the ink is quite expensive. It's a high quality output. It's similar to that of the laser printer, but it is very slow. It's good for single prints, things like photographs, and you can change the quality output for photographs. It's really very useful for things like home offices or for personal devices. You're not going to see them very much in offices because in large offices because the output, it's so slow, you don't get the fast printing multiple copies. It is cheap to buy the printer, although the ink is more expensive to run. And then we've got the dot matrix printer, very rarely seen these days, but they are still used in certain functions. Okay, much lower quality. It's quite slow and quite noisy. It's what we call an impact printer because the image appears as a result of a pin physically hitting the paper through an ink ribbon. The benefits of this is it actually uses continuous paper. There's this roll of paper that can be fed in, and it's just continuously dragged through. It doesn't use different sheets. And because it uses impact, it can also produce carbon copies. So where you have two sheets of paper, and when you write on the top one and you separate them, you can see it on the underneath piece of paper. That's called a carbon copy. And you can print like that on dot matrix. The other benefit of dot matrix printers is that they're very robust in dusty or dirty environments. So if you're working in a garage or in a building site or a factory, and you just need to be able to produce simple printouts like orders or receipts or labels to go on a specific delivery box or whatever else, the dot matrix printer is fine for those needs. Doesn't have to be high quality output, and they're far more robust. They're not going to break as easily as the inkjet or the laserjet if they were to be bashed or damaged or to get dust inside them. And then we have the plotter. Plotter produces really very high quality, very large printouts, things like billboard posters, buildings, or building blueprints. It is quite slow to produce these, but because of the size of them, obviously, very expensive to maintain. You do have two types of plotter. You've got this kind of the drum plotter here, where you have a big roll of paper coming through. Looks like an old mangle where people used to dry their laundry. Or there's the other type of this called a flatbed, which looks like a much larger version of a laserjet printer. But these are the 4 types of printers that you need to be familiar with. Okay, so that summarises for this morning's revision video, and I'll post again later on today for chapters 3 and 4, and then probably tomorrow morning for chapters 5, 6, 7 and 8.